only virtually, unfortunately. Always more fun to be in Flanders and in Belgium, indeed. I'm actually very close to you, just across the border. But let's get into the subject matter here and allow me to talk about something that I think is of significant interest, not only in AI, but also far beyond, namely cooperative competition. So here is a nice historical photograph from 1956 from the Summer Olympics in Melbourne, Australia. And this is a very typical picture that we see here. Well, of course, you know, the sports dress is a little old-fashioned right now, but the fundamentals haven't really changed, right? People compete in the Olympics, some win gold, and those tend to be very happy, like the chap here on the #1 spot of the podium. And even the #2 silver and #3 bronze, you know, they have achieved something truly outstanding, but look at their faces. They're much less happy than the gold medal winner here, right? And that is a very typical thing. So in our Western societies, we believe that competition helps us excel not only in sports, but also in industry, in science, indeed, and in computational solving problems, right? And the idea there is that, you know, we basically develop algorithms for challenging problems in AI and other areas of computer science. And whoever has the best algorithm, in a sense, wins the competition. And sometimes there are actual competitions, you know, problem-solving competitions. And these are really great because they help us assess the state of the art in solving a problem of interest. They provide an incentive to the participants in the community beyond for improving the state of the art. And they also often provide guidance to practitioners and the users of algorithms or systems or tools, you know, for what algorithm, system, tool, solver, in short, they should use for a given problem that they have, right? So for all these reasons, competitions are useful. I want to give you a concrete example from an area of AI that many of you might not be familiar with, so-called SAT competitions. I will talk in a moment about what SAT is, but you know, the SAT competitions are basically world championships for solvers for a problem known as SAT, which is the satisfiability problem in propositional logic. Now, you might say, why do I care about this? Modern AI is all about machine learning, right? This doesn't sound like machine learning. Why should I really care? And I will tell you in a moment. But before I do, let me give you a flavor for what kind of a problem SAT is. It's basically a little logic puzzle. So given an expression such as this one here, not x2 or x1, and then not x2 or not x2 or not x3, and a whole bunch of other conditions like this, where all of these variables, the x's, can take a value true or false. The question is this entire formula here denoted f, can we set the axis such that this becomes true, right? And in this case, that's the case, because if we set x1 and x2 to true, you can see that quite easily the first of these expressions here is satisfied. x1 is true, right? The second one here actually is not satisfied quite yet, but if we set x3, x4, and x5 false, then this is also satisfied by this little term here. This one here is obviously true again, made true by x1 and x2. This one here is true, made true by not x4, and this one by not x5. So the whole thing becomes true. And so the question is it possible for any given f to find such an assignment of variables? And that's what the SAT problem asks. Now, why is this relevant? Well, because there are very important practical applications. It turns out that if you can solve this little problem, actually much bigger versions of this problem, you can actually verify formally with mathematical guarantees the correct behavior of hard and software, which of course is of great importance. As a result, this problem has been studied for over 60 years in computer science and beyond. And there has been amazing progress in solver performance since the 1990s. In fact, this is one of the fundamental AI problems that is monitored for progress in the Stanford AI Index. And if you look at this, you know, and compare 2021 to 2017 even, you can see how much progress there has been. Strangely enough, people don't talk that much about it, which might be because, you know, the industries that use these kind of SAT solvers are mostly chip manufacturers, but actually all of them do that. And they're a little bit less outspoken about their successes than the big machine learning companies. So, competitions have helped advance the state of the art in solving many AI problems, not just stat, but also AI planning. And of course, in machine learning, there are competitions too, and in many other areas of AI. However, competitions also have a number of shortcomings. It has been demonstrated that they often suffer from noise and low statistical significance, which means that even sometimes if you repeat a competition under slightly modified circumstances, you get very different rankings of the participating algorithms or systems. They typically involve manual and out of context tuning, so that when you take a competition winner and use it on a real world problem, you're actually not guaranteed, and you can't even reasonably expect to see the same kind of performance ordering respective to other algorithms from this competition. And they are also mostly focused on single solvers, single algorithms, and broad spectrum performance across, whatever set of benchmarks are used in the competition. And as a result of this, they often actually do not reflect the true state of the art, and they also typically don't provide an effective incentive to improve the true state of the art. Now, this talk here is a bit of an appetizer, right? Not a full 7-course meal, and therefore we won't be able to talk about everything on this little laundry list here, but I will talk about the last point because, in my opinion, that's particularly important and insightful. And that is what gets us into this intriguing concept of cooperative competition. And the key idea behind this, and the key idea behind state-of-the-art solvers for many AI problems nowadays, is to leverage performance complementarity between different approaches for solving the same problem. And this can be done in at least 3 ways. The first of these are so-called parallel algorithm portfolios, or in machine learning, it's typically also called ensembles, which is where rather than just using one method, you use multiple methods in parallel and then somehow combine their performance or results together. This is not the only way. There's also algorithm schedules or pipelines where you run one algorithm after the other. And then there's finally, per instance, algorithm selectors where you look at the problem to be solved, you extract some features, and then depending on that, you choose one from a set of algorithms and run only that. Okay, so 3 different ways of leveraging the fact that some methods do better on certain kinds of input data, certain types of problem instances than others. So cooperative competition now is based on this idea of leveraging the strength of all competitors, not just one, with a goal of maximizing what you could call team performance, okay? And then, of course, also, you wouldn't want to reward just the individual algorithm that, basically gives you the best performance, but you want to reward contribution to this team performance. And I will talk in a moment about how this can be measured, but there are some pretty straightforward ideas. So here we are back in 1956 at the Melbourne Olympics, and I didn't tell you yet what competition that was. In fact, if we look at the same image from a slightly different perspective, here is what we see. Now, who are all these guys behind number 1 on the podium? Well, they are his team members, because that actually was the ceremony, the medal ceremony for the field hockey competition, which was won that year by India. And on the podium there is the captain of the Indian team, Balbir Singh Sr., a very celebrated field hockey player, right? But in reality, of course, Singh himself would have never won this tournament, right? It's his team that did it together. And so here is a more modern gold medal from the 2016 Olympics in Rio. So the idea now is basically that rather than giving one gold medal to Singh, right, we would cut up this gold medal and give pieces to his team members, depending on how much they contributed. That's the idea of cooperative competition. And this idea has been operationalized by people from my team in a series of events called Sparkle Challenges. They're called that because it allows everybody to shine, not just the one person who happens to get the gold. So the idea is that there is a competition platform to which these solvers of a given problem, such as SAT solvers or machine learning algorithms, are submitted, right? So every competitor submits their solver there. And then we built a per instance algorithm selector, a little engine that can choose which team member actually participates in solving a given problem. And which team member that is depends on the problem to be solved, right? So this is not like field hockey where everybody is playing, right? This is a lot more like a team sport where actually you have a team of participants, but you can designate one to compete at any given time. However, you can change that person depending on circumstances, right? A little bit more like a relay race. And so here we assess solver contributions to the overall performance based on something called relative marginal contribution that I'll explain in a moment. And then there is concurrent assessment and solver development during a so-called leaderboard phase. So in other words, during training, you can observe already what's happening. And ultimately, credit is given for contributions to the performance of this overall selector, and that goes to those people who actually authored the component solvers, right? And so this was first tried in the Sparkle SAT Challenge in 2018, which actually was part of a series of events called the Flock Olympic Games, where many different challenges were being held for logic-based AI solvers. And that was coordinated with the 2018 SAT competition, so the World Championship in SAT solving. It was launched in March 2018, then there was a leaderboard phase of 10 days in April that same year, and the final results were announced shortly thereafter. There were quite a few competitors, so actually in the field hockey competition in the Olympics 1956, there were only 12 teams. We did a little better here. We had 19 open source solvers and 4 closed source solvers that were included or concours, so they couldn't get any part of the gold medals, but they could contribute. For anybody who wants to look at details, the slides will be posted later. You can go to this URL here, but I'm going to share the highlights with you now. So what this Sparkle competition platform is actually using is it builds a team of solvers using an earlier engine that people in my team had constructed called Autofolio. And what that does is it automatically configures a flexible selector framework to find a state-of-the-art customized selector for a given situation, an algorithm selector, right? And so it was based on a well-known flexible per instance selection framework we had developed the year before, and leveraged under the hood a state-of-the-art general purpose algorithm configurator that essentially from many different configuration options can automatically and reasonably efficiently determine the one that gives the best performance. And that means that in Sparkle, we have cutting-edge and very robust automated selector construction. So how do we assess solver contributions? So we build a selector, we run the selector on certain problems. How do we assess how big of a piece of the gold medal every solver should ultimately get? And here's the idea. Given a set of solvers, let's call this S, and a per instance selector, that's the engine that selects which solver should be used on a given problem to be solved, and some set of problem instances to be solved, right? Some sets of inputs. We define the absolute marginal contribution by this expression here. And rather than parsing the math, I just want you to imagine a reasonable way of assessing the contribution of somebody to a team. And the easiest way to do that is you take the person out of the team and then assess team performance. And the drop in performance that you get when you eliminate one person from a team, or one solver in this case, that gives you an idea of the contribution of that team member, right? And this is exactly what is being formalized by this formula here. You can see here in the numerator of this expression, we take the solver whose marginal contribution we want to assess, we take that out, and then we divide this by the performance with it. And we do it this way because here we are actually minimizing running time. So lower values are actually better, okay? And then of course we can normalize this such that the marginal contributions sum to 1 so that we basically get fractions of the gold medal. And we do that by simply dividing by the sum of all marginal contributions. So before showing you the outcome of this competition, I want to show you a very interesting effect. So a traditional algorithm competition, such as the SAT competition, works by running all the solvers on a previously unseen set of test problems, a benchmark set, right? And then basically looking which of the solvers did best on that set. And that's what we call the SBS, or the single best solver. It's what will get the gold medal in the end, right? And so if you now look at the first leaderboard, so at the beginning of our leaderboard period where everybody could see how well everybody else was doing, this is the performance that we got. And these are CPU seconds, so low bars are good, right? Because it means less computation time for solving these problems. So you can see that during the leaderboard phase, the single best solver actually improved. And this is what you would hope, right? You would hope that as people see how well they're doing, they continue training or improving their solvers so that they actually get better, including the very best one, right? So training should help get better performance. That's the idea why athletes train on, for instance, the final course in some ski race as well. Good. And so then after the leaderboard, you get basically some final training performance, and that can be even better because unlike in sports, of course, outside of this competition framework, you can do more development and testing, right? So this is like in sports, you could do a few more runs on other ski hills, right? And improve your skills there. And then your final training performance would be even better. And then, of course, you get to do the real event. And at the real event, challenges might arise that weren't there during training. And of course, that happens here too. And you do a lot worse, right? That can easily happen. And it did happen in this case. So now the interesting thing is, if you could always magically, from all the competitors, for every single problem that you're solving, pick the best and have this magical choice of the best evaluated instead, of course, you would do far better, right? And indeed you do. And that too improves over the leaderboard phase. It improves even a little bit over the final period to the final training. And then some of this nicely translates actually in the performance on the final test problems, which of course are very different from the training problems, right? So this is interesting to see. And then our Sparkle selector, which of course isn't a perfect selector, it has to use machine learning to actually really choose realistically one of the competitors to run on that problem, right? It basically splits the difference a bit, right? And in the final testing, it doesn't quite get half, but it does get a notable improvement over the single best, which is good enough for us. So now to the really interesting result. So these bars here show you the performance, and I remind you that low bars are good because these are computation times. We want low computation times, right? These are the final standalone performance metrics for solvers. And what you can see there is that there is a few solvers here at the beginning of the pack that are quite nicely separated. Then there is a clump together that are basically tied. Then there's a few stragglers. And then there is a big performance drop to, a bunch of solvers that really don't compete well, right? So these are way, way behind. They take way longer to solve these problems, okay? And here is the virtual best solver, this perfect selector. And so now you can see if for every problem you could pick the best competitor, right? Then actually this is the performance that you would get. And this is, it's pretty amazing how well this works. Now, of course, in reality, you don't quite do so well. You get this real world selector, and that's still pretty amazing compared to the single best solver here. But that's what we've seen before. Now let's look at the marginal contribution, right? And the marginal contribution is shown here on the right-hand scale. You see a percentage marginal contribution. So that's the size of the slice of the gold medal that we gave to these solvers. This here is on training data, right? So what you can see is that yes, the number one solver in standalone performance does make an important contribution of just under 10%. But look at these guys who would be completely marginalized if we just looked at the podium. They also contribute, right? And look, for instance, at this guy here who contributes more than the number two solver, right? So way down there at the bottom of the top 10, you find a solver that contributes more than the number two solver in terms of standalone performance. And that's pretty amazing. And now if you do the same thing on testing set, you find basically exactly the same phenomenon, right? That solvers that are way down the ranking all of a sudden get a sizable chunk of the gold medal, which is really cool. So the final results on this, they show that you can actually close 14.3% of the gap between the perfect selector and the single best solver. So this is sizable improvement, but still leaves a lot of room for better machine learning for the selector and so on. And here you can see how this compares in terms of ranking, standalone rank versus the size of the chunk of gold medal that they get in the cooperative competition. And then also the relative and absolute marginal contributions, right? And what you can see here is that the one ranked first, right, actually also gets the largest slice of the gold medal in the end in our official results, right? With a relative marginal contribution of just under 13%. The second also compares nicely,
But the third rank, according to Slice of the Gold Medal, which is almost as large as the one ranked second, is the one that in standalone performance is only in 11th. So this is a specialized solver that on its own would have very little chance to do well. But as part of the team, it actually really pulls its weight. And if you go further down, you find many more examples of this kind of thing. Okay. So the advantage of these cooperative competitions, of these Sparkle challenges, of which we meanwhile also did another one for AI planning with very similar results, is that it makes it much easier to gain recognition for specialized techniques that don't work well across the board, but that work very well and might indeed work best under certain circumstances. These kind of competitions much better reflect and also make accessible the state of the art. The selector that is built by the Sparkle platform is actually sort of a meta solver that you can use, right? You can actually take this and run it on real problems. Now, it is just basically something like a delegator, right? It just says, this problem I'm going to give to this team member, this solver over here, right? Whereas that one goes to this one over here, right? So it's a distributor that sits on top of the actual solvers. But it's a real piece of software that you can run for real and that gives you real performance improvements by basically smartly selecting who should solve what. And we achieve that by leveraging synergy, complementarity, and these meta-algorithmic design techniques such as an automated selector. And that then, of course, provides an incentive to improve the true state of the art, right? If the competition is like the one that I've just outlined to you, right? Then no longer is my incentive to make a solver that does marginally better across the board than the best that is out there, such as number one compared to number two, according to standalone performance in the previous competition that I talked about. But now actually you can often make much bigger improvements by having a niche solver that on its own would do terribly, but together with everything else that's already there, improves the overall performance maximally that you can get when cleverly selecting who solves what, right? There are further benefits in that this makes it very easy to leverage performance complementarity. It promotes and ensures best practices in use and evaluation of these solvers, and it also improves reproducibility of these kinds of competitions because, you know, now there is a competition platform that does all of this automatically, including the selector construction and so on. And finally, using this kind of an approach, we can facilitate robust and trustworthy AI, which, as you all know, is not just a priority for the kind of AI program you have in Flanders and in Belgium, but for all of Europe and beyond. So finally, I want to make a little remark about learning and reasoning because of this asymmetry in the publicity that learning has been getting recently. And, you know, I'm actually deeply engaged in both, actually at the intersection between learning and reasoning. In my mind, these are really very closely connected, right? Human intelligence would be completely unthinkable without learning and reasoning, right? So we clearly need both. And in fact, you know, deep learning, which has revolutionized certain areas of machine learning, can be very nicely juxtaposed with what you could call deep reasoning, which is, for instance, SAT solvers like the ones that I mentioned earlier that can solve formulae with hundreds of thousands of variables and tens of millions of constraints on these variables. And so in particular, there is a nice connection which you get when you study the verification of deep neural networks. Verification properties such as this neural network here is robust against adversarial attacks or noisy perturbations of their inputs, right? And you can do that by using a generalization of SAT solving called SMT solving or SAT modular theory solvers, which are automated reasoning engines, or mixed integer programming, which are reasoning and optimization engine. Okay, and here is an example from most recent work out of my group. Without going into the details, this shows how you can exploit performance complementarity, such as the one that is underlying the idea of cooperative competition for deep neural network verification on the kind of data sets that are heavily used in the deep learning literature. And what you can see here, again, is the CPU time for verifying, which can be rather large indeed. So you see the CPU seconds here go up into the 10 to the 5, right? So these are actually very significant multi-hour runs that you have, and some of them time out as well, which is what you see here on the right and at the top. And what you can see is that here actually we use an ensemble. So we, rather than selecting, we just combine two different configurations of a solver together, but it's the same idea. And we get improvements, reductions in running time up to 2 orders of magnitude, and going from essentially thousands of CPU seconds to single-digit CPU seconds. And on average, of course, it's not quite as impressive because you run 2 things in parallel, so you always pay a performance penalty as well of a factor of 2. You still manage to reduce the running time very significantly by about just over 50%. So in a nutshell, competition is useful, not only in AI, but also far beyond. But success in the real world and also in real AI applications often depends on teamwork. And teamwork is not just between people trying to, program AI algorithms, but also between the AI algorithms themselves. For instance, in the context of automated selectors or parallel portfolios. Cooperative competition has as the key idea to compete not just for overall performance, but for contribution to team performance, right? So your goal in cooperative competition is to maximally improve the performance of the team that you're part of. And this is enabled by meta-algorithmic design techniques such as parallel portfolios, automated selectors, and algorithm pipelines and schedules, and the Sparkle platform that my group has been working on for a couple of years now. Also, and very importantly, cooperative competition does leverage human creativity, diversity of perspective, and complementarity of individual solutions to challenging problems by leaving essentially very little on the cutting room floor, right? It's not that everybody makes the podium, it's that, you leverage what is there in the team, and some contribute more to your podium than some others. And this is very important because, we live on this planet, and this is a very unusual top-down view right straight on the North Pole. And I'm sure that you're reading, aside from, rather disturbing news about the war in Ukraine and the pandemic, you're also reading about climate change and what's currently happening in the Arctic and Antarctic regions of our planet. And this is truly terrifying, actually. Against this, I have to confess, both the war and the pandemic are actually sort of peanuts, as tragic as that is, because what we are cruising towards here is a major, major ecological disaster that will impact the quality of life of people around the planet very, very drastically. And this is exactly the kind of problem that we can only solve with a teamwork approach and not with a winner-takes-all approach. And indeed, this is not a new insight. It has been around in computer science for a while. There's a very nice quote by Alan Turing, which I will not use today, that goes to this in this direction from 1948. And here's another one, which is actually from 1912 by one of the most influential politicians of the early 20th century. And it goes like this: competition has been shown to be useful up to a certain point and no further. But cooperation, which is the thing we must strive for today, begins where competition leaves off. And this was said famously by Franklin D. Roosevelt. So, I think we haven't internalized this message yet, but we ought to, because in AI, in society, and everywhere, this is something that can really help us tackle some of the challenges that we're facing. And with that, I thank you very much for your attention, and I'll be happy to take a few questions.